Okay, hey everyone. We're going to get into chapter 7 now, which is the beginning of inferential statistics. So this is the main act for this course. We're getting into the real heart of things, inferential statistics. And we're going to be doing something called confidence intervals, which you may have heard in the past and maybe not been quite clear on what it means. Unfortunately, you're going to know what it means after this. Okay, so this chapter is made of two sections, and in the first section, it's dealing with population parameters. Sorry, the whole chapter is dealing with population parameters. In the first section, it's population proportion. In the second section, it's dealing with population mean, mu. So we're doing sort of the same thing twice. Okay, so what we're going to do to teach you this topic, we're going to go through kind of one example, and it's going to take several pages. And we're just going to see all of the details through this one example. By the end, you should be able to construct a confidence interval for a population parameter and also be able to interpret it. What does it mean exactly? Um, in the next video, we're going to look at a bit more formally, like what are the requirements that you need for this procedure to work. We'll be a bit more formal about it. And then in the last video, we'll do using these ideas to work backwards and find the sample size. How many people do I need, or how many individuals, how many objects do I need to study in order to get a certain kind of confidence interval that I want? Okay, so right now we're doing basically a long example to just see how this all works. Okay, so COVID-19. Everybody's thinking about COVID-19. So suppose we want to know um, whether Canadians are willing to take a vaccine, to receive a vaccine for COVID-19. That's probably going to be on our horizons pretty soon. And with all the, I don't know, there's some controversy about vaccines. We might want to know, are Canadians willing to take the vaccine when it's available? So suppose and of course I don't have real data for this, but we're just going to use synthetic or made up data to investigate this. So suppose we select a simple random sample of 50 Canadians, just 50. And we ask each person if they would be willing to receive a vaccination for COVID-19 if such a vaccine were to become available. Hopefully it will eventually. And let's assume that 45 of those people say yes. And the remainder say, no, I'm against vaccines, or they say, I'm not sure. Okay, this is going to be quite a simple question here. What is our best estimate of P, the proportion of all Canadians who would say yes to receiving a vaccine if it were available? Okay, well, what's our best guess? Our best estimate of P is P hat. Our best estimate of the population proportion P. P is just P hat, which is the sample proportion, which is 45 over 50, which I think it comes out to 9.9, right? 90%. And why? Why is that our best guess? I mean, it's the only guess we can make, you might say, from the data we have. But why is that the best number given the data we have? Well, it's the best guess because p hat is unbiased. P hat is an unbiased estimator. Of p. In other words, the distribution of p hat, whatever the distribution of p hat is going to be centered on p. This is the distribution of p hat. We know that in theory, the distribution is centered on p. So whatever we get for p hat, it's going to be the best we can do to estimate p. Okay, so that's called a point estimate. Just that one number is called a point estimate. It's just one number, right? One number. Now, the truth is that one number is not that useful by itself, right? I find that out of 50 people, 90% of them are going to say yes to a vaccine. But how do I know that? How do I know that that reflects the whole population? It's only 50 people. How far could it be from the truth? Well, in theory, it could be completely wrong, right? We could have randomly picked the only 45 people in the country that were willing to take the vaccine, right? And maybe the true percentage is almost zero, or maybe we happen to find 5 people who would say no, and those are very rare. Maybe in the whole population, it's closer to 100%. Because of the randomness, almost anything is possible for getting p hat. The question is, what are we usually going to get? How far will p hat be usually away from p? How far? Let me say it again. How far away from the truth, from p, will p hat be usually or typically? That's what we really want to know. Okay, so we're in order to deal with that, we're going to be doing confidence intervals. Okay, so let's imagine that somehow we know the true population proportion. Somehow we've asked everybody, yes or no, vaccine, and this is the proportion of people who say yes for the whole population. Now, is this realistic? No, but there's some proportion, right? There's some true number. We just don't know what it is. Let's imagine that it's this number. So if that's the true proportion, describe the distribution of X, which is the number of Canadians who respond yes in a random sample of 50. Well, we know that that X is going to be a binomial random variable with probability of success. I misspell probability all the time. With probability of success being p equals 0.895. And how do we know it's a binomial random variable? So we should just at least think to ourselves, fixed number of trials, so fixed n, 50. It's success or failure, which is yes or not yes. Same probability p, and independent. The only one that's a bit tricky is independent. How do we know that these selections are independent? It's because 50 is much less than 5% of the 37 million Canadians, right? So the sample size is less than 50% of the population, so we can assume it's independent. Okay, so it is binomial probability of success p. What is the mean value of x? So we're asked here, describe the distribution of x. So what's the mean value? We'll call that mu x. What's the mean value for a binomial random variable? It's going to be n times p. That's 50 times 0.895. What is that? 44.75. Okay, so a little bit less than what we observed, but not that far off. What's the standard deviation? Sigma x for a binomial variable that is npq. So square root of 50 times 0.895, and q is the probability of failure. Let's just do 1 minus 0.895. Don't have to think too hard. And what do we get? 2.1676. And that goes on. Okay, so that's the distribution. And let's just make a quick sketch. What does that look like? So it's going to look like, okay, maybe I won't draw it with that yet. I'll draw the rectangles first, because we know it's actually a binomial. It's actually a discrete distribution, right? So the most likely value for x is probably going to be 45, because that's the closest whole number. remember the mean value doesn't have to be actually one of the possibilities. It's just the average in the long term. But we can tell that the most likely value is going to be about 45. So the distribution is going to look something like that. And we know that from the central limit theorem, we know that this lines up very nicely with the normal, I shouldn't say very nicely, it lines up relatively well with the normal distribution. Let's check that. From the central limit theorem, we know that x is approximately normal with the same parameters. Mu is 44.75, sigma is 2.16766. And there's a condition here though, right? As long as what? As long as, now, be careful here. So when we did the general central limit theorem, the conditions were, we did two cases, right? We did one for sample mean, and then the conditions were that x should be normal, or that n should be greater than 30. But that's not what the case we're in right now. We're in the binomial case, and so the conditions there were n times p has to be at least 5, and n times q has to be at least 5. So here, what is n times p? Well, n times p is, we just did that, 44.75. What is n times q? So here we're actually cutting it close. It's going to be 1 minus 0.875, and that comes out to just 5.25. So it's just barely larger than 5. But it does meet the requirement. Okay, so out of a sample of 50, we're most likely to get 45, and then it drops off from there. The width from the mean out to the inflection point, that's sigma, and sigma is about 2.167. So that means I did this about right. It drops off around 47 or so, right? Okay. Now, that's the distribution of x. Why are we looking at the distribution of x? Because it's very closely related to the distribution of p hat. Let me show you why. Now, on the next page, this is just a nicer version of what I just drew. So this is, why did I do this again? I don't know, but it just looks better. So this is the number of people who say yes out of 50, and we can see that the most likely value is here 45, and it drops off. So I'm just pointing out here that the normal distribution is not that great of an approximation, right? It's reasonably good, but it disagrees with several of these by quite a lot, right? So it's off by a fair bit here. So why is it off? It's because the normal approximation is only moderately good because those requirements are just barely being met. Because the requirements are just barely met. Barely satisfied. So these red things are the error in the approximation. Okay, but that's not our biggest worry. Like that's not a big deal. It's not going to stop us at this point. Okay, so I said the distribution of x is related to the distribution of p hat. Why is that? How is that? So same example, same assumption. It's still 89.5% of people would say yes. describe the distribution of p hat, the proportion of Canadians who respond yes in a random sample of n equals 50. So in other words, it's the sample proportion. P hat is the sample proportion. Now, and we're going to sketch it. Now here's the key observation. Note that p hat is the number of successes divided by, I'm going to use a capital letter X here. It's the number of people who say yes divided by the sample size. That's a close connection, right? X is this distribution, p hat. It's going to be very similar. It's just we're dividing it, we're going to divide by n. And what that means is the mean value of p hat, it's just going to be the mean value of x divided by n. Why is that? If every x value, let's say we get 45. What's the most common value of x? 45. What's the most common value of p hat? It's going to be 45 divided by 50. Every time we divide x by n, every time we divide x by n to get p hat, so the mean is just going to be divided by n. So that's going to be, what was the mean value of x? It was n times p divided by n. So it's just p. Okay. Now, what about the sigma? So let's do the variance. So sigma squared of p hat is going to be, now this is a little different. Sigma squared is going to be the sigma squared of x divided by n squared. Divided by n squared. I had to think about that for a second. And why is that? And if you watch the video from section 6.6, I did have a discussion of this, but let me repeat it very briefly here. The variance is a quadratic function. It's a power of 2 function. Variance is a quadratic function of the, I'll just say a quadratic function. So if I divide, so dividing x by n means that the deviations x minus the mean squared get divided by n squared. To calculate the variance, we're squaring everything. And so if that dividing by n becomes dividing by n squared. I know it's a little bit brief of an explanation, but maybe you can trust me on that. And so what is the sigma for p hat? It's going to be just, I'll take the square root. And so I get sigma of x divided by n. What is sigma of x? Square root of npq divided by n. Now, what is that? So I can simplify that a little bit. Let's see, I'll break it into two steps. I'll split that up into square root of n times square root of pq. And I feel like we need a different color here. Now what? I can cancel this, and I just get square root of n on the bottom. So it actually is pq divided by n, all inside the square root. So that is the, let's summarize it here. So sigma for p hat is the square root of pq over n, which is very similar to the binomial random variable sigma. It's just divided by n. Okay, the last thing is that the central limit theorem tells us that p hat like x is normal as long as the same conditions are true. And n times q is greater than 5. It's the same conditions because it's going to be the same shape. It's just going to be, everything's going to be divided by 50. So I what if I can make a little bit more space for myself? I'll clean that up later. I want to draw a sketch of the distribution. So I'll do that over here. You'll see it in the same position later. So the distribution of p hat is going to be also normal, and its mean value is p, which in this case is 0.895. And I'll draw in these rectangles to suggest that this comes from the x distribution divided by n. And in fact, p hat is a decimal, but it really is a discrete random variable because there's only 51 different possibilities for p hat, if you think about it. So then the sigma here is npq. No, I said that wrong. pq over n, which is what? We didn't calculate that, did we? Let's actually finish that. What is that? It's 0.895 times 0.105, which is q, divided by 50, which is what? Square root of that, 0.04335. So think of that as approximately 4%, right? What this is saying is that the distribution of p hat is, think of it as 89 point, it's a mean of 89% plus or minus 4%. So p hat is going to be within about a 4% margin of error, maybe 8% if we want to capture more of the possibilities. Okay, we're getting really close to the confidence interval now. Okay, now so now we're going to carry on with this example until we're going to get to the actual confidence interval definition. Okay, so we're looking at the distribution of p hat, which is up here. And so if the true value is the same as before, we're going to use the normal approximation to determine the interval into which p hat will fall 95% of the time. So let's draw that distribution one more time. This is the p hat distribution. Here's the true mean in the middle. And we know that this is, what do we say, 4%, so 0.0433, what was it? 335. So what I want to know is what interval contains 95% of the outcomes for p hat. 95% of the outcomes, I should say, what interval contains p hat for 95% of all outcomes? That's the right way. Now, what should we do? Well, we're going to use Excel, so let's keep in mind that if this is 0.95 in the middle, then each of these tails here is how much? 5% left over divided by 2, so 2.5%, and this is a 2.5% tail here. So what is this p hat value right at the edge? What is this p hat value right at the edge? We could call those critical p hat values. That's not a term people use a lot, but they're the sort of limit of what defines typical or usual. So how do we find that? Well, the lower p hat, we can do it with Excel. What is it now? We're going to use the normal approximation. So it's norm dot inverse of the area up to that point, which is 0.025, comma. Now what else do we have to give norm inverse? We have to give it the mean value, which is 0.895, and we have to give it the sigma, 0.04335. Let's see what we get. So I'm not going to flip my screen over, but I'll just do that on the side here. So what is it? 0.025, 0.895, 0.04335. I get 0.8100, 0.8100. So 0.8100. So that's kind of the lower end of normal, or the lower end of usual. What about the upper p hat? Now this one's a little trickier because I need to give it the area to the left. It's not 1 minus norm, it's still norm inverse. It's going to be 1 minus 0.025 because it's all the area except for the right tail. And then the same mean, same sigma. And what do I get? Let's see, I'll just go back here. I'll just change. Oh, actually, I just realized when I switch screens, you can see the screen. So it's different from Collaborate. So I don't have to manually switch the screen. So I'll just copy this, paste it here. And I'm going to change that to 1 minus that. Okay, 0.9799. Oh, let's round it to, if I round it to 4 places, it'll be 0.9800. 0.9800. So that's the upper end of what we might expect. So what is this saying? This is not a confidence interval. Don't think that yet. This is if we somehow knew the true mean, if that was really the true mean, we would expect p hat to be between these two. P hat is between these two for 95% of all possible samples. That's what we're saying. Now, okay, let's keep going. So to get further with this, we need to transform this normal distribution into a standard normal distribution. Okay, so what I'm asking now is, what is the z-score for these limits here, these two upper and lower limits? So well, let's remember, what does z-score mean here? The general formula for z-score is it's the value minus the mean divided by sigma. So in this case, it's going to be the p hat value minus the mean p hat value divided by sigma for p hat. So the lower one is going to be 0.8100 minus, what's the mean? 0.895 divided by, what's the sigma? We know the sigma, 0.04335. And just think here, so what should we get? What should we get for the z-score? It should be about 2, right? Or negative 2, actually. Because for 95%, empirical rule says it's 2, or negative 2. So let's make sure, hopefully that's what we get. And divided by 0.04335. Okay, and it is close to 2. It is not exactly 2. It's negative 1.961. We'll round it to 3 decimal places here. Actually, I'll just do 2 decimal places. Okay, so that's close to 2. close to -2. And then the upper one is, now maybe you can guess this without even doing the calculation. I'm not going to say what it is yet. So it's that upper p-value minus the mean divided by sigma. What is the z-score? The z-score is how many sigmas away is it, right? How many standard deviations away is it? 0.895. How many standard deviations away is it? 1.96 plus 1.96, which is close to +2. So that's exactly what it should be. So 1.96 is the more precise version of the empirical rule. So let's try to summarize what that's saying. So an equivalent way to find the interval into which p hat falls for 95% of samples. So the equivalent way to do what we just did here would be to first find the interval into which the test statistic z falls for 95% of samples, where this fancy word test statistic z just means the z-score for p hat, which is p hat minus what is the mean of p hat? It's p. What is the sigma for p hat? It is square root of pq over n. So we call this is a z-score, and let's say we know that, and this is normal. This is a normal variable. This is normal. Not only is it normal, it's actually a standard normal, because we've this is called normalizing, or we're standardizing. When we subtract the mean and divide by sigma, it makes it a standard normal with its own mean value, 0 and standard deviation of what? 1. And that's true as long as p hat is normal, which is true as long as what? As long as those requirements at the beginning are met. And n times, okay, so we're getting deep into it here. This test statistic z should be a standard normal variable as long as these requirements are met. It should be a standard normal. So we know that for a standard normal, the z value lies between, we're going to call it minus z subscript alpha over 2 and plus z alpha over 2 for a fraction 1 minus alpha of all so I should say with probability. That's probably a better way to say it. With probability uh, 1 minus alpha. Now let me draw you a picture. Why am I using this alpha business? So here's my standard normal, and I want to say that this middle area is going to be 1 minus alpha. So let's say if alpha is 0.5, i.e. 5%, then 1 minus alpha is going to be 95%. So this is kind of a generalization of it doesn't have to be 95%. It could be a different probability. So this tail will have area the leftover part is alpha, so each tail has to be alpha over 2. This one's also alpha over 2. Area alpha over 2. Let me use red for these numbers so they stand out. This has area 1 minus alpha. This is area alpha over 2. And so these Z values are called critical Z values. This is called Z alpha over 2 because it has this area to its right, and then that same number but negative is the left side. So running out of space here. Let's see if I can make this spread out. Oh, we can. All right, so what was I going to say? Oh yeah, so if I use 5% for alpha, what is Z alpha over 2 in that case? Well, that would be Z 0.05 divided by 2, which is Z 0.025. What is the Z value that has an area of 2.5% to its right? It's the Z value with a right tail of 2.5%. So how do we do that? Well, with Excel, it's going to be norm.s, standard, dot inverse, times, or not times, and I give it the probability what? Not 2.5%, because that's to the right. I need it to the left. So 1 minus 0.025. What do I get? It should be 1.96, right? 1.96, hopefully, equals norm.s.inverse 1 minus 2.5%, 1.9599, 1.96, 1.5996. 1.95996, which is, we'll round off to 1.96. So, conclusion here. What's the conclusion? What we know is that for 95% of all samples, of all outcomes, let's say, I know that Z is between, I'm going to call it Z alpha over 2, which is this number, but I want to keep it as a symbol for the moment, and negative Z alpha over 2. Now, we're trying to get back to p hat here. I didn't realize I have to write so much here. What is Z? Therefore, what is Z? Z was just p hat minus p over square root of pq over n. That was the definition of Z. It's the Z score for that sample proportion. And therefore, if I do a little bit of algebra here, if I multiply everything by pq over n square root, multiply everything through by pq over n square root, and therefore now if I add p, so then I get p minus the critical Z value. So what I've done is I'm adding p to all three things, right? Adding p to all three expressions. So then what I've achieved here is it's still not a confidence interval, believe it or not, but it's going to be the same interval that I did up here. Let's plug everything in and see if we got the same interval. So p hat should be between, what is p? 0.895. What was the Z value? 1.96. What was this? 0.895 times 0.105 divided by 50. And on this side, same numbers. 1.96, 105, 50. And let's see what we get for those two numbers. I'm just going to pause here, do it, and then I'll write them down. So you can pause too. Okay, and what I get is that p hat is less than 0.97997 and greater than or equal to 0.8100277. If we round that to 4 decimal places, it's the same as, whoops, it's the same as above, right? The same as the, let's label it star, and let's go back, I'll label that one star. That was this, right? Same numbers. So why did we do this whole complicated detour through the z-score? Well, by dealing with the test statistic, in the past, dealing with the test statistic allowed us to just work with standard normal distributions and not with general normal distributions. That was the main advantage. And this test statistic approach is going to help us in the next section when we do the sample means. It's not going to be Z anymore. It's going to be called something called a T distribution, but it's not that different. Okay, so we are almost there, almost there. Now, what we just found here, we have found, so carrying on, we found that for 95% of all samples of size 50, the sample proportion P is within a margin of error E, this is a new term, margin of error E of the true population P, where E is, it was this expression that that was the plus or minus amount, right? That's this thing is, this is the margin of error. So here we did, so i.e., if we do P minus the margin of error, that's the lower limit for P hat. And if I do P plus the margin of error, that's the upper limit. So that's what we found. And another way of saying that is that this means that P hat, I should have made this a little smaller. And what this means is that P hat is within a distance E of P. So we're gonna, if this is our grand conclusion, P hat is within a distance E of P 95% of the time. With, let's say, with probability 95%, but here I have an alpha, so what I mean is 1 minus alpha. That's our grand conclusion. And if we just change this sentence slightly, it's that if I say, I'm within a distance of 5 meters from you, then that's the same as saying that you're within a distance of 5 meters from me, right? So imagine I draw, here's P hat, and that's me, I'm P hat, right? And let's say you're within 5 meters of me, you're P. That's the same thing as saying that I am within a 5 meter distance of you. And so that's the way that concept of distance works. And that means I can say, that implies that P is within a distance E of P hat. So if I switch these two things, it's the same thing. P is within a distance E of P hat for 95% of all samples. So what we can say then is that P is in the middle now, is less than or equal to P hat plus E, greater than or equal to P hat minus E with probability 1 minus alpha. Okay, we're just about there. There's one last thing. Here's what we have to do. We have to stop pretending that we know what P is, right? At the very beginning, we said, okay, let's imagine P is 0.895, but we don't know what P is. So let's stop pretending that we know what P is. And how do we deal with that? All we know is that for 95% of samples of size 50, P is within a margin of error E of P hat, where E is Z, the critical Z value, P times Q over N, which means, i.e., P is between the, it's at most this distance above P hat, PQ over N, or it's at most that same distance below P hat. So where in here did we assume that we know what P is? The problem here is that in here we assume that the value of P is known and Q. Same here. We can't actually calculate these things unless we know what P is. And that's the problem. So what we do, statistics is all about doing the best we can with the knowledge, information we have. Since we don't know P or Q, the best thing we can do to estimate the standard deviation of P hat, which is this thing, is to use P hat and Q hat in that formula. So here's what I'm saying. We use P hat instead of P, and we use Q hat instead of Q, because we know P hat and Q hat, and that choice to use those sample statistics instead of the true parameters is we give that the name standard error. So the standard error of P hat is denoted SE of P hat. It's the same formula but using P hat and Q hat. So what was P hat? If you think all the way back, remember what was P hat in this case? It was 45 out of 50, which is 0.9. It's a little different. It's not 0.895, it's 0.9. This 0.895 was just a made up number, right? We just made that up. I don't know what it is. What is Q hat? Then it's going to be 1 minus that. And so we may as well calculate what that is. 0.9 times 0.1 divided by 50 square root, 0.0424. It's still about 4%. 0.0424. It's not that different. So using this approximation is not a big deal. It still works just fine. So finally, we obtain the 95% confidence interval for P. We know that P is between P hat plus Z alpha over 2. And here, let me break it down. So instead of, here we write SE. We're using the standard error of P hat. You'll recognize it in a second. So that's the same thing as P hat minus Z alpha over 2, P hat Q hat over N, P. So that's the one this is what we want to know. This is the unknown thing that we're trying to trap. Okay, so this last line, that is called a confidence interval. It's the interval into which we think the true P falls with a certain probability, depending on alpha. So if we choose alpha equals 5%, like we've been doing, then Z 0.025 is, we know, 1.96, and then the interval is then the 95% confidence interval is, well, let's put all the numbers in. So it's the p-hat value minus 1.96. We're estimating the standard error using that p-hat value. And plus 1.96. And p we don't know, so it just stays p. Let's see, what do we get? Let me calculate the margin of error, which is the last term, first, and then I'll use that. So it's about 8%. Whoops. It's 0.9 plus the margin of error, 0.831. So this is called the margin of error, E. And on the other side, it's the same thing, but minus the margin of error. So that's also E. And so what do I get? It's 0.9 minus that number, 0.817. So usually for intervals like this, we round to 3 decimal places. That's the kind of standard. Okay, so 3 decimal places. So that becomes 0.983. So final answer, if we ask 50 people and 90% and 45 of them say yes, then we think that the true proportion for all of Canada is going to be between about 82%, 81.7%, and it could be up to 98.3%. That's a pretty wide range, right? That's not a very useful number, maybe. So what would we do? Probably go back, make a larger n, and then we would end up with a narrower interval. Okay, so that was kind of a long one. I hope you took a rest in the middle and maybe watch this again if after taking a bit of a break. And in the next video, I'm going to just say all of this again in a very compressed way, a bit more like what the textbook does. But I wanted to give you all the gory details here for those of you who really want to understand it. If you really study these notes, I think you're gonna know confidence intervals inside out. See you in the next video.